Welcome. Today we're going to dig into something called heteroscedasticity.
Right.
Sounds a bit technical, maybe, but it's really important for making sure we can trust our data analysis.
Absolutely. It's a core concept.
So our mission today is basically to get a handle on why the, let's say, scatter or variability in data isn't always consistent.
Hmm.
And, what that really means for the conclusions we draw. We'll try to keep it clear. No need for advanced stats degrees here.
Exactly. So heteroscedasticity fundamentally just means the spread or variance of the errors in your model isn't constant across your data.
Errors meaning like how far off our predictions are.
Precisely. Think about predicting house prices.
Yeah.
Your model might be pretty accurate for small standard houses,
Okay.
but for huge unique mansions, the potential error, the difference between prediction and reality, could be much, much larger and more varied.
Ah, I see. So the wiggle room changes.
That's a great way to put it. And yeah, that changing wiggle room can really affect how reliable everything is.
Okay, so where else might we see this in, the real world?
Oh, lots of places. Like the sources mentioned, income versus spending is a classic.
Right.
Lower income folks, their spending is often pretty predictable, right? Mostly on necessities. But as income goes up, spending becomes much more variable. Some high earners save loads, some spend extravagantly. That widening spread, that's heteroscedasticity.
Okay, that makes sense. Any other examples?
Sure. Think about measuring something. Maybe reaction times. People might be quite consistent on simple tasks, but on complex ones, the variability in how long they take could increase quite a bit.
Yeah.
More room for error, more spread.
Gotcha. Now, I saw mentions of pure versus impure heteroscedasticity. What's that distinction about?
Good question. So pure is when this uneven variance is just inherent in the data. Like the income example is just how things are.
Okay.
Impure heteroscedasticity is, well, it's often our fault, so to speak. It suggests our model might be misspecified, meaning maybe we left out an important variable or used the wrong functional form, like trying to fit a straight line to a curve. The model itself is causing the uneven errors
And knowing the difference matters
because it tells you how to fix it. If it's impure, you might need to improve your model first. If it's pure, you look at statistical techniques to account for it.
Right. So how do we actually, see this in data? Are there visual clues?
Definitely. Visuals are key. The most common way is to plot the residuals.
The errors, basically.
Exactly. The difference between your model's prediction and the actual value. You plot those against your predicted values or against one of your input variables.
And what are we looking for?
You're looking for a pattern in the scatter. If the points spread out more as you move along the horizontal axis, like a cone or a fan shape,
Ah, the fanning pattern.
that's the classic sign of heteroscedasticity. Or they can narrow too. The point is the vertical spread isn't constant.
Okay, a fanning pattern. Good visual cue. Now, the big question, how does this unevenness actually impact our results? What does it break?
Well, here's the tricky part. It doesn't usually make your main estimates, your coefficients, biased. On average, they might still be right.
Oh, okay, so what's the problem then?
The problem is efficiency, and crucially, are standard errors. The estimates become less precise. Think of it like your aim is right on average, but your shots are scattered wider.
So less reliable estimates.
Less precise, yeah. And because the standard errors which measure that uncertainty get calculated incorrectly under heteroscedasticity.
They're usually underestimated, right?
Often, yes, they're wrong. Which means we think our estimates are more precise than they actually are.
And that messes up our hypothesis tests.
Exactly. Your t-statistics, your p-values, they all rely on having correct standard errors. If those are wrong, your tests are wrong.
So you might think a result is statistically significant when it isn't.
Right, a type I error, falsely rejecting the null hypothesis.
Or you could miss a real effect.
That too, a type 2 error. Your test might not be powerful enough to detect a genuine relationship because the noise is obscuring it, or rather, your measure of noise is inaccurate.
So basically, ignoring this can lead you to draw completely wrong conclusions from your analysis.
Pretty much. You get a false sense of confidence, or you miss important findings. It undermines the whole inference process, making decisions based on that. Risky.
Okay, definitely something to watch out for. Now, you mentioned statistical fixes earlier. Can we touch on those briefly? What can be done?
Sure. The main approaches involve adjusting how the estimation is done. Methods like weighted least squares, WLS, or generalized least squares, GLS.
The gist being.
The idea is to give less weight to observations that come from the more variable parts of your data, the noisier points, and more weight to the ones from the less variable parts.
Kind of like focusing more on the clear signals.
Exactly. Or, alternatively, you can stick with standard ordinary least squares, OLS, but use robust standard errors, sometimes called Huber-White standard errors.
And those,
They're calculated in a way that's more reliable even if heteroscedasticity is present. They don't fix the inefficiency, but they give you more accurate hypothesis tests.
got it. So there are ways to manage it. And this isn't just an issue in, say, economics, is it?
Oh, no. It pops up all over. Time series analysis, definitely. Think about stock market volatility. It's rarely constant, right? It changes over time. That's heteroscedasticity in a time series context,
Oh,
often called RCH or GXCH effects.
interesting.
And even in machine learning, some algorithms assume constant variance, and if that assumption is violated, their performance or interpretation can be affected.
So wrapping up, the key takeaway is this thing called heteroscedasticity, this uneven spread of errors, it's more than just a statistical term. It can seriously impact how much trust you should put in your statistical findings, even if the main results look okay on the surface.
Precisely. It's a reminder to always check the assumptions behind your models. Don't just look at the final numbers.
That's a really crucial point. Okay, final thought for everyone listening. Given how variability seems to change in so many different situations, not just data sets, where else might this kind of unequal noise be affecting our understanding, maybe leading us astray without us even realizing it? Something to think about. Thanks for this deep dive.